Hello viewers, my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. So today we are going to discuss the topic, the problems on maximum usable frequency. So today we are going to discuss the topic on maximum usable frequency, the problems, and these problems and the topic are related to the course antennas, waves and propagation. So these problems are related to the course antennas, waves and propagation. Let us start our session. So before going into the problems, let us see some basic definition of a critical angle and maximum usable frequency. What actually is maximum usable frequency and what is this critical angle? Here the critical angle, it is the angle of incidence at which a wave is returned to the earth at a minimum distance. The angle of incidence at which a wave is returned to the earth at minimum distance, we call it as a critical angle. So here, there is another formula to find out the critical angle. So the formula of critical angle, it depends upon the height of the anospheric region. So here, sin theta c is equal to h by h square plus d square by 4 whole power half here. So sin theta c is equal to h by h square plus d square by 4 whole power half. So here h represents the height from earth to the ionospheric layer. And d represents the distance. D represents the distance between the transmitting antenna and the receiving antenna. And here there is another definition for a critical angle. That is the angle of incidence in denser medium from which the angle of refraction is 90 degrees. We call it as a critical angle. Here generally what actually is critical angle, let us have how to find out the critical angle. So how to find out the critical angle, we will see here. Let us assume here there is a boundary here. Here there is a boundary here, and here whose refractive indices are different from one medium to other medium. This is 1 and this is 2. And here let us assume a normal is drawn here, and let us assume a electromagnetic ray is traveling towards the normal. When a ray is transmitted from denser medium to the rarer medium, when a ray is transmitted from the rarer medium to the denser medium, here the angle of refraction, there is some refraction is happening here. Assume this angle as 20 degrees. Again, if you take another 1 and 2, there are two mediums here, medium 1 and medium 2. Now here the ray is traveling from rarer medium to the denser medium. So here what happens? We are increasing from 10 to 20 degrees. The angle of refraction increase. Here the ray bends towards the boundary. So this is the boundary. This is the normal here. So when a ray is traveling from rarer medium to the denser medium, it moves away from the normal. And it is moving towards the boundary. Again, if you draw a ray, if you increase the ray, again if you increase to 30 degrees, again the ray bends like this. There is a refraction. This refraction is happening. And here this is the boundary. So here as the angle of incidence, this is the I value. So the angle of incidence here, this is the I here. As the angle of incidence is increasing, the wave is going to bend away from the normal. So at one point what happens? Here when you increase the angle to 40 degrees, the ray becomes parallel to the boundary here. So this 40 degrees is known as the critical angle. This 40 degrees is known as the critical angle, denoted by the symbol theta c here. So here the angle of incidence at which the angle of refraction is 90 degrees, we call it as the angle of critical angle. So this is how to determine the critical angle. So this critical angle determines upon the surface of the ionospheric region, upon the height at which the ionospheric layer is present, and also the distance, between the transmitting antenna and the receiving antenna. Let us do the problem here. The first problem is the radial communication is to be desired between two places here with 1000 kilometers as the distance of separation. The communication is desired via an ionospheric layer with a height of 400 kilometers above the Earth's surface. If the frequency of the transmitter is varied beyond a certain frequency, then the strength of the received signal becomes negligible. Calculate the frequency if the critical frequency is 11 megahertz. If the critical frequency is 11 megahertz. So let us see the problem. The radio communication is desired between two places with 1000 kilometers. So the distance between the two places is given as 1000 kilometers as the distance of separation. The communication has to be established between the transmitting antenna and the receiving antenna, and the signal is going to touch the ionospheric layer with a height of 400 kilometers above the Earth's surface. So here the ionospheric layer height is given as 400 kilometers from the surface of the Earth here. If the frequency of the transmitter is varied beyond certain frequency, then the strength of the received signal becomes negligible. So calculate that frequency. The critical frequency is 11 megahertz here. So let us write the data here. So here at the receiver, the signal strength is negligible. So if the at the receiver the signal strength is negligible, it means that no wave is received at certain frequency. So in other words, the wave which penetrates the ionospheric layer will return to the Earth. So here, what is actually the MUF means? So what actually the MUF, that is the maximum visible frequency. Here, suppose let us assume here there is a transmitting antenna and here there is a receiving antenna. Here for a fixed distance we are going to calculate the frequency. So here when we transmit the signal with 5 megahertz, the signal is going to touch the layer. It is coming here. Now if we transmit the frequency another with the 10 megahertz, it is going to travel and reach to the some point here. A, this is B. If we transmit the 15 megahertz with the frequency of 15 megahertz, it is going to reach to the receiving antenna. This is C here. So here the distance is fixed here. The distance is fixed here. So here the maximum visible frequency is nothing but the frequency at which a wave is returned to the surface of the Earth for a given distance of propagation. We call it as maximum usable frequency here. So we call it as maximum usable frequency here. So here, if the frequency of the transmitter is varied beyond certain frequency, so here the frequency is varied beyond certain frequency, it is nothing but MUF. That is the maximum usable frequency. So here we need to calculate the maximum usable frequency if the critical frequency is 11 megahertz. So the critical frequency is 11 megahertz. So for the given data, so we are going to find out here the solution for this. So here, what is the given data here? F MUF. We know that the critical frequency is given as FC. The critical frequency is given as 11 into 10 power 6. It is given as 11 into 10 power 6 here. And the D distance is given as 1000 kilometers. And H is given as 400 kilometers. So H is given as 400 kilometers here. So this is what the data is given. So from this we need to calculate the F MUF value. F MUF value. F MUF stands for maximum usable frequency here. So here the critical frequency is given as 11 into 10 power 6. So what is critical frequency? The frequency at which a wave is returned to the Earth at vertical incidence. We call it as the critical frequency. So here, suppose this is the curved surface of the Earth and there is a layer. Let us assume this is a D layer and we are going to transmit a signal. We are going to transmit a signal vertically. The signal goes and returns to the earth here. So here the angle of incidence, is 0 here. The I is equal to 0 here. So for critical frequency, the angle of incidence is 0 here. So here the frequency, the maximum frequency, the highest frequency at which a wave is returned to the surface of the earth at vertical incidence, we call it as a critical frequency. So here in our problem, the critical frequency, it is given as Fc is equal to 11 into 10 power 6. So we are having a formula based upon F of Fc into square root of d by 2h whole square plus 1. So this is the condition for flat earth. This is the condition for flat earth here. Now let us substitute the values here. So Fc is given as 11 into 10 power 6 into square root of 1000 kilometers divided by 2 into 400 plus 1 here. So if you simplify this 2 zeros get cancelled. So this is equal to 11 into 10 power 6 divided by 10 by 4 2s are 8 here plus 1. So this is equal to 11 into 10 power 6 divided by, this is 8. 10 plus 8 means 18 here. So here 2 4s, 2 9s here. So square root of, you will get 11 into 10 power 6 into square root of 9 by 4 means square root of 3. 9 is equal to 3 and by 2 here. So this you will get approximately, if you simplify this, you will get 17.608 megahertz. So this is the value we are having. So here F muff is equal to Fc into root of d by 2h whole square plus 1. So in this problem, all the data will be given here. So only what we need to know is, we need to know only the formula, that is the relationship between the maximum usable frequency and critical frequency. So F muff is equal to Fc into square root of d by 2h whole square plus 1 here. Now let us do the second problem here. Find the critical frequency of the region at a height of 200 kilometers above Earth's surface. Assume that the radio communication link has to be established between the 2 points on the Earth 2000 kilometers away from each other, and the maximum usable frequency for this distance is 30.6 megahertz. So in the previous problem, we have determined the value of muff. So in this problem, already the muff value is given and the distance is also given here between the 2 points. So the 2 points are nothing but the transmitting antenna and the receiving antenna, and we need to find out the critical frequency. So we need to find out the critical frequency. So as per the data given, what is the value of H here? H is equal to 200 kilometers. Assume that the radio communication link has to be established. So we need to transmit a signal between 2 points on the Earth, that is a transmitting antenna and receiving antenna, which is a distance of d is equal to 2000. What is the distance here? It is 2000 kilometers away from each other, and the maximum usable frequency for this distance is 30.6 megahertz. So the maximum usable frequency, we denote it as muff. This is equal to 30.6 megahertz. So what we should find out here? So we need to find out the critical frequency of the region at a height of 200 kilometers. So the critical frequency, it is given by Fc is equal to, we need to find out here. And we are having an equation. We are going to determine this from the equation here directly by substituting the data. So here H is equal to 200 kilometers and F muff is equal to 30.6 megahertz. It is given, and by use the formula here, F muff is equal to Fc into root of d by 2h whole square plus 1. So here from this value you can find out the MUF value is given as 30.6 into 10 power 6. So this is equal to Fc into root of, the value of D is given as 2000 kilometers. So the value of D is given as 2000 kilometers divided by 2 into 200 whole square plus 1 here. So if you simplify this, you will get Fc into root of, this is 2000 by 400 means 200 ones, 200 tens, 2 ones. This is 5 square plus 1. So this equal to, you will get Fc into root 26 here. So this is 30.6 into 10 power 6. So what does this implies? The critical frequency is equal to 30.6 into 10 power 6 divided by root 26. So root 26 is nothing but 5.1 something. So here root 26 is equal to 30.6 into 10 power 6 divided by 5.1. So this equal to approximately, you will get 6.001, which is approximately equal to 6 megahertz. So approximately equal to 6 megahertz here. So this is how to determine the value of critical frequency. That is, the critical frequency Fc is equal to, you are getting 6 megahertz. So this is the data given here. We are finding Fmuff value here directly by the formula Fc into root of d by 2h whole square plus 1. Substitute the data given in the formula, and for mathematical simplification you will get Fc is equal to 6 megahertz approximately. Now let us calculate the critical frequency of the E layer if its average density is 0.96 into 10 power 11 per cubic meter. Calculate Fmuff if the angle of incidence is 20 degrees. So here we are going to calculate the critical frequency, and average density is given as N. So the average density is given as N max. N max indicates, N stands for density. So maximum ionization density or average density, it is given as 0.96 into 10 power 11 here. So from this value we should find out the value of critical frequency. Also we should find out Fmuff. So there are two things to be determined in this problem here. Now we know that Fc is equal to 9 root N max. Fc is equal to 9 root N max here. So what is here 9? 9 into root N max, 0.96 into 10 power 11 here. So if you simplify this, 0.96 into 10 power 11, Fc is equal to 2.846 megahertz. So like this, the formula between the relationship between the critical frequency and the average density of ionization is given by Fc is equal to 9 root N max. So 9 into root of 0.96 into 10 power 11, so you will get 2.846 megahertz. And similarly, there is a secant law. So what is the secant law here? Fmuff is equal to Fc secant theta I here. So the theta I, it is given as 20 degrees here. So what is Fc? We know that Fc, the critical frequency is 2.846 megahertz into 10 power 6. What is secant theta I? Secant theta I is equal to secant 20 degrees. So if you simplify this value, you will get 3.0286. So you will get 3.0286 megahertz here. So here, this is a very simple problem. So again I repeat here. Here it is given as N max. N max is given as 0.96 into 10 power 11. And we need to find out the Fc value. And we need to find out the Fmuff value. The angle of incidence, it is given as 20 degrees. So Fc is equal to 9 root N max. So this is equal to 9 root 0.96 into 10 power 11. So this is equal to 2.846 megahertz. Similarly, MUF is equal to FC secant theta I. So FC secant 20. So FC is nothing but 2.846 into 10 power. FC is equal to 2.846 into 10 power 6 into secant 20. So this is equal to, you will get 3.0286 megahertz here. Megahertz. So this is how to simplify the problem. So you can see here the data given. So n max equal is given as 10 power 11. This is not 10 power 11. It is 0.96 into 10 power 11. Here 0.96 into 10 power 11. So substitute the values here and simplify the by mathematical simplification. You will get the value of FC and FMOF. So here there is another problem. Assume that the reflection takes place at a height of 400 kilometers and that the maximum density in the ionosphere corresponds to 0.9 refractive index at 10 megahertz. So what will be the skip distance for flat earth for which FMOF is 10 megahertz? So we need to find out the value of skip distance. We need to apply some formula here. So here, what is the given data here? Height is 400 kilometers. Refractive index is 0.9 is given as, and frequency is given as 10 megahertz. And FMUF, it is given as 10 megahertz. So we need to find out the value of D here. We need to find out the value of D here. So what is D here? We know that what is the, there is a relationship between FMUF and FC here. So we know that FMUF is equal to FC into root of D by 2H whole square plus 1. So here we do not know the value of FC here. We do not know the value of FC here. So we should find out the value of FC. So FC is equal to 9 root N max. But we do not know the value of N max here. So we need to find out the value of, this is equation 1, this is equation 2. So what is N max? We do not know what is the N max here. So there is a relationship between the refractive index and the N max. So mu is equal to root of 1 minus 81 N by F square. What is the value of mu here? 0.9 here. So the value of mu, it is given as 0.9 here. So 0.9 is equal to, this is N max. This is equal to 1 minus 81 into N max by F square means 10 into 10 power 6. So if you simplify this, you will get the value of N max. So the N max value, so we will get as 0.23 into 10 power 12 per meter cubed. So N max is equal to 0.23 into 10 power 12 per meter cubed. Now this N max value you should substitute in FC here. If you substitute in FC, you will get the value of FC here. So FC is equal to 9 root N max. This is equal to 9 root N max. What is the N max value? 0.2345 into 10 power 12. So just now we got the N max as 0.23 into 10 power 12. Substitute this value here. If you simplify this, you will get 4.3588 megahertz here. Now based upon the FC value, we should find out the value of D. D skip. D skip is equal to 2H into root of F muff by FC whole square minus 1. So this is the condition for flat earth. So D skip is equal to 2 into, we got the value of H is equal to 400 into 10 power 3 kilometers. We got 400 kilometers, 400 into 10 power 3. So the value of F muff is equal to 10 into 10 power 6. It is given in the data. And what is the value of FC? The critical frequency, we know that 4.35 into 10 power 6 whole square minus 1. So if you simplify this, if you simplify this value, you will get 1651 into 10 power 3 meters. So this is the D skip. So d skip is equal to 1651 into 10 power 3 meters. So here we need to, for solving this problem, we should know the value of d. So d is equal to 2h into f muff by fc whole square minus 1. Here we do not know fc. fc is equal to 9 root n max. Here we do not know n max, so we should know the formula of mu is equal to 1 minus 81 n max by f square. So we know, if we know these three formulas, then we can just easily simplify this problem here to find out the value of d skip. So this is for flat earth. Suppose we want to do for curved earth, the formula is 4h into f muff by fc whole square minus 1. This is for curved earth. This is for curved earth here. So here f muff by fc whole square minus 1 here. So you can see here in the problem, mu is equal to 1 minus 81 n by f square. Substitute the value of 0.9 here. From this, you will get the value of n max. So n max equal to 0.2345 10 power 12. And here, if you simplify, there is no square root here. You will get 4.3588. And for substitute this fc value in the d skip formula, 2h into root of f muff by fc whole square minus 1. If you simplify it, you will get 1651.8 into 10 power 3 meters here. So for references for these problems, you can refer U.A. Bakshi and also K.D. Prasad, Antennas, Waves and Propagation. Let us close the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.